Spearman correlation, Pearson correlation, and Kendall-Tau correlation. Now today we will be continuing with biserial and point biserial correlation. So as already I've told that biserial correlation are used when one of your variable is dichotomous, and if that dichotomy is continuous dichotomy, means there is some continuum between the two groups, then we will use biserial correlation. Otherwise, if the dichotomy is uh, discrete, not having any continuum, which is in many cases, maximum cases will find this kind of dichotomy. That is, there is a discrete dichotomy. In that case, we will do point biserial correlation. Method remains the same. Only what we do that we denote it by RB or RPB. If it is like we denote the Pearson correlation with R, so this one we denote by RPB if we are doing point biserial, or RB if we are doing biserial. So through this we actually denote that our one of the variable was categorical or dichotomous variable. So is my screen visible?
Yes, sir.
Fine. So please open a data, rather import because it's a SAV file, pbcore.sav. Once done, please let me know. Once you are done with the data import, please let me know. Have you opened this data pbcore.sav? I have already shared this data. Its name is pbcore.sav.
Yep.
Done? Okay. Ready with the data?
Yes.
Okay. So we'll focus on these two variables, time and gender. So this is the time spent out of home in minutes, and this is the gender, male and female. So here we have coded uh, 0 as females and 1 as males. And we want to know what is the relationship between the gender and their time spent outside, whether gender has any association with time spent outside. So you can see this is our continuous variable time in minutes, and gender is categorical dichotomous variable with no means continuum in between. We have discrete dichotomy. So if we have to check this relationship and our data is like this, that one of the variable is dichotomous, then we will choose on biserial or point biserial correlation. Further, we will see that the dichotomous data is discrete or continuous. So this is the discrete dichotomous variable. So we will choose, we'll go for point biserial correlation. And the method of correlation will be the same, the Pearson one. Only the reporting will be different. So regression, correlation matrix, and we will choose our time and gender. So we got a correlation coefficient of 0.378, but we will denote it by RPB. So this one actually will be subscript. So RPB is equal to 0.378. So there is 37.8% of positive correlation, means as the gender changes from 0 to 1, the value of gender changes increases from 0 to 1, the time spent out of home also increases. That simply means here you can see we have coded 0 as females and 1 as males. So simply we can find a correlation that yes, gender has the relationship with time spent outside of home, and males tend to spend more time out of home as compared to females. Is this clear? May I have from audience? Is this clear? The point?
Yes, sir.
So simply we'll say that as the time spent out of home increases, as the gender changes from 0 to 1, the time spent out of home increases. And here 1 stands for male. So we can say that these two are correlated, and males tend to spend more time as compared to females out of home. Now let's test it with this another variable where we have recorded the gender. We have named this variable as record. Now here we have made 0 as male and 1 as female. Let's see what happens. Again, you are getting the same value, but negative correlation. Means as gender changes or increases, time spent out of home decreases. Coefficient is same, 37.8% or 0.378. Only this has become negative. This signifies, again, now remember here what we have recorded, 0 as males and 1 as females. So it is saying that as gender value increases from 0 to 1, time spent out of home decreases. Again, see, you are getting the same result, means 1 stands for female. So for them, the time spent out of home decreases. And for males, again it increases. So even if you record it, then also you will get the same result. The correlation will be negative, but result overall interpretation will remain the same, that males tend to spend more time out of home. Is this point clear?
Yes, sir.
Okay. Now let's clean this, and we will now do another kind of correlation, that is partial correlation. As I have explained the partial correlation concept, here you can delete all these variables. Partial correlation is used when you want to check the relationship of between two variables, but there is also a third variable that is influencing this relationship, and you want to control that variable or keep it constant. In that case, we apply partial correlation. Like I have given you an example, the correlation between the increasing the knob burner, means increasing the flame, and uh, the time taken by water to boil. So here in this case, what will happen, that the time taken by water to boil will decrease as the flame increases, but it will not be always the case. Suppose if you have taken ice cold water, then it will be a different relationship. The time will the time will be more. So you need to keep the initial temperature of water same for all, so that you get a standard correlation. So in that case, you have to control the amount of water, you have to keep a control on the initial temperature of water. These are the extraneous variables, and you need to have a control over this. Third variable influencing this relationship. So when you have to control any variable, then we apply partial correlation. So again, you open that first correlation file, exam anxiety.sab. So here we have already checked a correlation between revision, exam, and anxiety, or how anxiety affects the exam performance. Now we want to measure this relationship. We have seen was influenced by revision. We want to know the relationship between exam and anxiety, exam performance and individual's anxiety. But previously, when revision was there, this relationship was affected because revision was having a negative impact on anxiety. More and more people revise, anxiety goes down, in turn, exam performance increases. Now we are interested in knowing the relationship between anxiety and exam while controlling for revision. We want to make revision constant, control it. So in that case, we will do a partial correlation. When we want to control the third variable and want to know only relationship between the two variables in presence of the third variable which is in controlled form. So you can select from here partial correlation and take exam anxiety and see the correlation value. It's minus 44, minus 0.441. But what is its, will it change if we bring in the revision and as a control variable? See, if we put, now we'll put revision as a control variable. See now what is the relationship? Simply see, initially there was a negative relationship between anxiety and exam performance. If anxiety increases by 1 unit, exam performance decreases by 0.44 units, or if 44.1%. It was decreasing. Now when we put revision as controlled variable, now what is the effect of anxiety on exam? It has decreased. Now if anxiety increases, exam performance only decreases by 24.7% when revision is controlled. Is this clear? The concept of partial correlation, is this clear?
Yes, sir.
So simply if you see the relationship between exam and anxiety, it will be minus 0.441. But there is a third variable also that might affect this relationship. Let's control it and see what is its impact. When we have controlled this revision, what is happening? Now the relationship has changed. Previously, when anxiety was increasing by 100%, exam performance was decreasing by 44.1%. Now it is decreasing by only 24.7%. So there is some improvement in exam performance when you have controlled the revision time. Clear? So if this is the case
Yes,
where
sir.
you want to keep any of the variable as controlled variable, then we go for partial correlation and we control that variable and then see the relationship. Now, in, now we are done with the correlations. Now we will move on to regression. So Any idea on regression? Can any one of you give me some idea? What idea do you have about regression?
Sir, in regression, we try to predict the cause of an event.
Okay.
We
Anything else?
we predict the future.
It is a predictive analytics technique.
Yes, sir.
Anything else? Why we call it a linear regression?
So there should be some kind of relationship between the variables. Then only we can predict ki in what direction it will go. When one changes, in
There,
what direction
there's,
another will change.
there should be a linear relationship, not only relationship, a linear relationship. And there we try to put the entire equation of regression, we try to fit it on a straight line. Is
Yes,
that
sir.
it?
Yes, sir.
Okay. This is actually a regression. And just a minute. Now, uh, I have already told you one concept that every outcome is equal to model plus error. So, my screen visible.
Yes, sir.
Outcome y is equal to model plus error. Model is nothing but the statistical model. So if you take the case of correlation, it will be Dx plus error. This will tell you about the correlation. But if you want also to predict the y based on the variables, then again we put one constant in this called B0. Now, this is the regression equation. This B0 is nothing but we call it basically now this is the formula y is equal to B0 plus Bx plus error where this B0 is the intercept. So it will tell you the value of y even if x is equal to 0. Let's assume if B0 is not here and the value of x becomes 0, then the value of y will also become 0. You can't predict the value of y. So for that purpose, we put this intercept, a constant B0, so that we can be able to predict y even in the case if x is equal to 0. So this is the intercept and this B is the regression coefficient of x or the gradient or slope of a regression line, and it also shows the direction or strength of the relationship. And this intercept is the point at which the regression line crosses the y-axis. You can see it like this. So this is the case where you have same intercept, different gradients. Because intercept is same because two different gradients are touching these two straight lines are touching at the same point. So the intercept is same, but gradients are different. Here the gradients are different, but the gradients are same. They are moving in the same direction, but touching at different points. So different intercepts are there. So if you fit the equation on a straight line and see that whether you have the same intercept and different gradients or same gradients, different intercepts. Normally, if you have many predictors, then you can have different gradients also. Okay. But if you have one variable, then normally you will have the same gradient, but intercepts, and if they are touching at different points, then touching the y-axis at different points, then the intercept will be different. And if you have more than one variable, then the same formula will become y is equal to b0 plus b1 x1 b2 x2 to bn xn and so on. This is actually a regression. Now, few things are important before we move on to regression. First one is that you should know that none of the question can 100% predict the outcome. None of the variable. That's why what goes unexplained, we mention it as error or residuals. These residuals are positive residuals or negative residuals. See, this is the arrangement actually. So if you are fitting the data points of the equation on a straight line, few of the data points will be away from this straight line. They won't be able to explain your variance. That's why we call them as residual errors. Those which lie above this line, they are called as positive residuals, and those which lie below this line are known as negative residual errors. So above this straight line are what the data points that are deviating from this straight line are in upward direction. They are positive residual errors, and data points that are lying below this uh, straight line, they are known as negative residual errors. So first assumption for linear regression is that there should be normality of residual errors. This is the first requirement. Here we don't check the normality of the data, we check the normality of residual errors. Normally in SPSS or in Jamovi also, we check it through normal QQ plots or normal PP plots. But in coding softwares like R and Python, we have because there is one more statistic for this checking of the normality of residual errors. Since it's a multivariate, if you are having many uh, this variables, many dependent variables, many independent variables, then that will make it a case of multivariate multiple regression, which is a type of multivariate analysis. So in that case, if you have to check the normality of residual errors, you have to check the this multivariate normality of residual errors. In that case, we use another statistic called Anderson-Darling test. Rather than Shapiro-Wilk or Kolmogorov-Smirnov, we use Anderson-Darling test. But that is available in R and Python only. In SPSS and here it's not available, so we can check it through normal QQ plots or quantile plots or probability plots. So this is the first assumption. Second assumption is that there should be no homostaticity, there should be no heterostaticity. So that you can check through Levin's test of homogeneity. Third thing is that there should be no autocorrelation, particularly in case of multiple regression. Means particularly when you are taking a time series data, then it's become very important that there should be no autocorrelation, which we check through Durbin-Watson test. I'll write it here. Assumptions of regression. First, normality of residual errors is checked through normal Q plots or normal PP plots or Anderson-Darling test. Second is no heterogeneity should be there. Homostaticity should be there. This is tested through Levin's test of homogeneity of variances. Third one is no auto correlation tested through Durbin Watson. Then this is of such importance, no multicollinearity. Why it is important? Let's say you have variable x1, x2, and x3. No multicollinearity means that there should not be high correlation between the independent variables. Because if they have, let's say you have three variables x1, x2, and x3. What will happen? Suppose x2 is unable to explain the y, your outcome, but still it is in the model, it is explaining because it is having high correlation with x3. So it is borrowing its property from x3 and showing its effect on y. It is show that actually it is unable to predict y, but it is predicting y because of its correlation with high correlation with x3 or high correlation with x1, and that's why you are keeping it into the model. Actually, it is not predicting y. So your model will be wrong. So this is very important that there should be no multicollinearity. This we test through variance inflation factor, VIF, and tolerance value. So VIF should be less than 10 and TV should be greater than 0.2. Greater than 0.2. If VIF value is between 1 to 3, then it's highly desirable. There is no problem of multicollinearity. If it is up to 5, between 3 to 5, still it is acceptable. Above 5, it shows some problem of multicollinearity, and above 10, till 10, from 5 to 9, there is some problem. But the moment it is 10 or above that, then there is a serious problem of multicollinearity. So these four are the basic assumptions that should be kept in mind while doing regression. Now, second thing is there are different methods of regression. And this explains that how you are entering your variables. These methods tells you about different methods of entering your independent variables or predictor variables. One is forced entry. In forced entry or in SPSS, you might be seeing by default enter method. You put all variables at once and you are letting the software to decide that which of the variable should be regressed first, because all cannot be regressed. So it will regress first, means one first dependent it will regress dependent variable upon the independent variable. So the dependent variable will be regressed upon that independent variable that explain my maximum variance. So what will happen? You are letting software to decide. So let's say you have three variables, and first variable is able to explain the variance to a level of 60%. It will take the first variable. Let's say third variable is explaining the remaining 40%. So the moment 100% variance is explained, it will drop the second variable. Though second variable might be important, but since the 100% variance is achieved or maximum variance is achieved, what it will do, it will drop the second variable. because you are letting a software to decide which variable should be entered in what order. And before testing on this, you should also check on that what variables you have to choose, because a variable, outcome variable, can be explained by many variables, many independent variables, but whether all are relevant. Let's say in our case, we will do on a data set album sales, where a music company owner is interested in predicting sales of the album based on three variables. First variable is advertising budget in thousand of pounds. Every unit is in thousand of pounds. We know that advertising has direct relations with sales. So this could be a variable of interest. Second variable is number of times that song is played on a radio, that album is played on a radio. How it is, how it can predict the sales. Yes, number of times it is played on a radio, people will come to know about the album. So sale might increase, it might affect the sales. Again, this could be a variable of interest. Third variable that we have taken is popularity of the band that have created that album. So if the band that has created that album is very famous, very popular, it could explain the sales of the album. But suppose we want to bring it into cost in producing the cost involved in producing one album. Will it, is it a variable of interest? May I have an answer? We want also to, apart from these three variables, we also want to look into how Y is explained by cost involved in producing an album. Should this be our variable of interest? May I have quick answers? Just a random thought. It might affect, but it is not that much important, because we are not interested in knowing that what will be the cost involved in producing an album. Indirectly, it might affect. Cost might, if the cost involved in producing album is high, it might affect the final price of the album. Maybe due to high cost, the price is very high of the album, and it will affect the sales, but not directly. So if we are bringing in this variable, it's of no use to us. So when you are choosing your variable, please choose your variable for predicting any outcome variable Y. Please choose the variables which are supported by strong literature review. So your literature should tell, from various studies, you should zero down upon, don't take many variables, take only those variables which are relevant. And this is where we do something wrong. We choose our variables based on our own choice. Better, always better to choose those variables which are supported by a strong evidence of literature or other studies. So first thing is that you choose your variable cautiously. Second thing is choose the method of regression. So let's say if you have chosen enter method, you are letting the software to decide based on maximum variance explained. What is the real problem? Let me help you with this method. Let me tell you with the help of an example. Let's say there is a cold weather outside. You have jackets, you have shirts, you have jeans, a pair of jeans, and of course undergarments also. If you will ask the software that what should I wear first so that I could be protected from this cold weather outside. So based on maximum variance explained, it will tell you that first you should wear your jacket. Then above jacket you should wear your shirt. And then above shirt, because maximum variance is explained by jacket, that will protect you from cold to the maximum. So it will suggest you that first wear jacket, then wear shirt, and above that please wear your undergarments. Overall, it will protect you from cold. But is this a good model? Of course not. So never let the software decide which variable should be regressed first, unless that method, forced entry method, is there. It should be used only in cases where you are unable to determine by yourself that which of the variable could be the strong predictor. So rather than software choosing for you, you should choose by yourself. And then we use another method, stepwise regression, where we are hierarchical regression, where we choose which variable will come first, which will be regress second, based on our choice supported by literature. If you are letting software to choose it, it will choose based on a mathematical calculation. And as I told you, this cold weather and the jacket example, so it will tell you to regress first that variable which is explaining maximum variances. Chances is that some important variable might be left out. Model might not be a good fit. So to avoid that, if you have done extensive literature review, if you are sure that which of the, because this is the step which I have seen many people skipping. They don't focus on this method of regression. Only simply just they put all variables at first. If you are not sure that which of the variable will be explaining maximum variance and should come first in the order of regression, then of course you can let the software choose through forced entry method. But if you are sure, please use your own method of entry, and this could be stepwise or hierarchical regression. So having said this, let's do one example. So please open a file albumsales.ca.sav and let me know once you are up with the file. Once you have opened the file, please let me know.
Yes.
Okay. So this is containing four variables. This sales is our dependent variable. Advertising spent, each unit is in £1,000. The sales also is in thousand of units. So this is the advertising budget. This is the album sold. This is the airplay, number of times in a week that the song was played on or the album was played on radio. And this is attractiveness or popularity of the band that created that music album on a scale of 10. So let's first do only simple linear regression. And in that, I'm taking only one variable, advertising budget, and its effect on sales. How it can predict the sales? So go to linear regression. Select the dependent variable, that is sales, and factors is here in covariates. You select your advertising budget. Now see, What is the value of R here? This R is nothing but the correlation. Now, how much variance can be explained? That will be told by R square. So first thing that the predictive model that we are making that can explain only variance to the level of 33.5%. Second thing is that what is the model? So B0 that is 134.13 or you can round it out to the nearest distinct. So 134 plus here I'll write if we put into B0 plus B1 X1. So Y album sales Y is equal to B0 that is 134 plus B1 that is the regression coefficient of the the variable that is advertising budget 0.0961 0.0961 into advertising budget. It's a simple linear regression model. Since 33.5% is explained, rest 67% around is not explained. So that is not explained due to this error term. Now let's check this by using other variables. This is simple linear regression. The moment you bring in more than one independent variable, method remains the same. The case becomes the case of multiple linear regression. So airplay attractiveness. Now here, this is the model builder. What I have done, I have forced, I have done forced entry here, letting the software to choose which of them will be regressed first. So I'll change it. I want here, since from literature review, I know that advertising has maximum effect on album sales. So I will choose first advertising. So first in the new block, add new block, first will be advertising. Second is airplay and attractiveness. In this case, I am not sure that which of these will be, let's say I am not sure that out of airplay, I am very sure that maximum variance will be explained by advertisement. So I have taken, I am doing hierarchical regression, stepwise regression. So I have taken advertisement in the first block. Means first this will be regressed. If I am sure whether airplay or attract will be the next one, then I will, let's say airplay, I'll choose in block 2 by clicking on add new block and attractiveness in block 3. But I'm not, let's say I'm not sure. So these two I will put together in another block. So airplay and attract both. So this is how I am building my model through hierarchical regression in 2 steps. Or if you are sure about the 3 variables differently, then you can choose 3 steps or 4 steps and like that. Now reference level, no need. Assumptions. We want autocorrelation test, collinearity, and QQ plots of residuals. Model fit, R square, adjusted R square, and F test. So R square and adjusted R square, we are getting 2 values. Now see, if you could see here, we have got regression in two steps. And we will also check the R square and adjusted R square. So you can also see when we have taken in the second step, when we have entered the variables, now the maximum variance explained has increased from 33.5% to 66.5%. Now more variance is explained. Now we can explain y or predict y to the level of 66.5%. Then model fit we test through F ratio, F value. That's how you get, when you do in SPSS regression, you also get a ANOVA table. This ANOVA table is nothing, it tells you, because again, ANOVA table is based on sum of squared loadings. So it will tell you about the fitness of the model. So for model to be fit, the F ratio should be, or F value should be greater than 1, and it should be significant. In our case, you can see this is 99.6% and significant also. So the model is fit. Second indicator of the fitness of the model is adjusted R square. We report R square, please remember, we never report adjusted R. Adjusted R square is only used to cross-validate our model. Whether our model can be generalized, because this is a model that we are doing on a sample of 200 observations. We want it to generalize it to the population. Let's say if we take randomly 200 other samples from the population, whether this model will stand fit or not. Because ultimately our aim is to make a predictive model that should stand correct in all cases in the entire population, because we are predicting something. We are not predicting only on the 200 samples. We want to predict it for the future also. We want this prediction model to be generalizable. So this will be told by adjusted R square. So if there is no much difference between R square and adjusted R square, then you can say that your prediction model is cross-validated. It will stand valid whenever you will draw any random sample from the population. Means it can be generalizable to the model. This model could be generalizable to the population. That will be told by adjusted R square. So if there is much difference between R square and adjusted R square, then your model is not generalizable. You have to check on your variables. Similarly, if your F value is less than 1 and is non-significant, then also your model is not fit. So these two are the fitness of the model. And what is the model? The model in our case is album sales Y is equal to first B0 minus 26.61 plus 0.84, or round it off to the nearest decimal, it will be 0.85 into advertising budget plus B2, that is 3.37 into airplay plus 11.09,863, we are rounding it off to the nearest decimal, into attract. This is our model. We will put the values of advertising budget, airplay, and attract here, and we will get our how many albums sale will happen, that we can predict. Now, if you see this, it is telling me that if advertising budget is increased by 1 unit, it will predict, means 0.085 units of albums will be sold, and these are in thousand of units. So if we spend 1,000 pounds, the album sold will be 85. Then it is telling that if you increase the airplay by one more time, then 3.37 units of album will be sold. Means 3370 albums will be sold by increasing airplay. Means one more time, if you play the album on radio, it will increase the sales to 3,370 unit pieces of album will be sold. If attractiveness of the band is increased by one unit, it will lead to 11.09 units of album sold. That is 11,090 albums sold. Now, out of these three, on which of these factors should the album company owner should focus on more? Thousand of pounds spent on advertising is yielding 85 albums sold. One more time airplay done is yielding 3,370 albums sold. And if the attractiveness of the band increases by one unit, let's say it was 7, it increases to 8, then it will lead to 11,090 albums sold. Which out of these three factors, on which of the factor the album company owner should focus more?
Attract airplay.
Why not attractiveness, sir? Because one unit change in
Yeah,
attractiveness.
that's what I said. That's what I said. Attractiveness and airplay, both.
Both. See, advertisement, he is spending 1,000 pounds and getting only 85 albums sold. Maximum albums are sold when attractiveness of the band is increased. But whenever we provide solution, we do not focus on the best solution. There is always the best solution, but there is always an optimal solution too. We should focus on the optimal solution. Here, if you see, spending on advertising is not yielding much. Attractiveness of the band is yielding very high. But the problem is, if you are focusing on attractiveness of the band, let's say you are choosing a band that is having high popularity, then won't it charge too much to the album company owner for producing the albums? Getting my point?
Yeah.
Sorry?
Yes.
If you are going for a very high popular album, it will charge again, again it will incur cost to you. Or if you are trying to increase the popularity of the band, you have to do a lot of advertisements, conduct shows, concerts, again to the album company. It will be a huge amount. Though attractiveness of the band is the best solution, but see, the optimal solution is airplay. Less investment because playing one more time won't cost much on radio. One time of airplay is yielding 3,370 albums. With least investment, he can get maximum yield. Isn't it? Am I correct or not?
Yeah.
Because airplay, playing one more time on radio won't have much, won't cost much. But in return, it will give 3,370 albums. But if you are choosing a highly popular band, then of course this is the best solution. But again, it will cost too much. So you have to see where you are getting maximum yield. So total album sold will be explained by all these variables. So I am not saying that he should drop others. He should have he should spend something on advertising, some amount on airplay, then fairly attractive bag, but maximum focus should be on the airplay. More and more he should promote it on the radio. And overall, all these will predict the total album sold. Is this clear? Is this point clear?
Yeah.
Yeah, okay. Now let's check for the assumptions. So fitness of the model has been established. What is our model we have established? What could be the best solution? What could be the optimal solution? Also, we have seen whether the model is generalizable to the population or not. That also we have tested. Now let's see for assumptions. As I told, for any assumption coming to be true, the p-value should be non-significant, it is greater than 0.05. So if you see the autocorrelation through Durbin-Watson, your p-value is greater than 0.05. So there is no autocorrelation. Then if you see the variance inflation factor and tolerance value for multicollinearity, already I have told that its VIF value should not be greater than 10, and between 1 to 3, if it is, then it shows no problem of multicollinearity. In all the three cases, you can see it is very close to 1 only, 1.01, 1.04, 1.04. So there is no problem of multicollinearity as indicated by variance inflation factor. Tolerance value should be greater than zero point 0.2. In our case, it is 0.986, 0.959, and 0.96 respectively. So it is greater than zero point 0.2. This also assumption fulfilled. Both the metrics of collinearity statistics indicates that there is no problem of multicollinearity. Now let's see the normality of residual errors. See, most of the data points are along this straight line. Only few are deviating. That means that there is a normality of residual errors, which we have checked through QQ plots. Right? So our assumptions, all four assumptions also fulfilled. And our model is also, we developed our model and we also found that our model is a good fit. So this is all about a regression. For further analysis, if you want to save them, you can save the predicted values for each. You can save the residuals. All these things you can save as a variable. So this is the fitness of the model. We can also see, normally we see it in this value AIC, AKK information criteria in logistic regression. But here also, if you want to see, you can see what is AKK information criteria. Normally, it is used in logistic regression, and this value should not be more than 100 actually. So this is multiple regression. We won't check this. Normally, we check through R square, adjusted R square, and F statistics. Then multicollinearity and all these things we check. So on all parameters, our data shows that the predictive model stands good. So this is about regression. And if any query is there, I am available to handle have that query.